Alrighty, ladies and gentlemen, let's go ahead and talk angular velocity real quick, okay? So we just finished talking about angular position today in class. Now we're going to introduce this concept of angular velocity. So in order to talk about this, we first need to talk about angular displacement. Now, angular displacement is simply the change in the angular position, which angular position is referred to as theta. So that'll give us theta final minus theta initial. All right. Now, again, there are many similarities between circular motion and linear motion. So as we calculated average velocity as being the change of position over the change in time, we're going to calculate the average angular velocity as being, so I'll write this, the angular velocity as being the change in angular position over the change in time. All right. Now, from this expression right here, we can derive our instantaneous angular velocity. All right. So if we look at that instantaneous angular velocity, just like we did with velocity, average velocity, we're going to take the derivative of this. All right. So a derivative, remember, is just taking a really small section of the graph and finding the slope of the line tangent to that point. So really what we're doing here is we're taking the limit as the change in time goes to 0 of our change in angular position over our change in time. And we're going to say that this is equal to omega. Now this omega right here is what we're going to use to represent angular velocity. All right. Now, the limit as delta t goes to 0 of the change in theta over the change in time, this is just simply equal to the derivative of the angular position with respect to time, which is equal to our angular velocity, omega. Now, this omega is going to be kind of a new concept for us. And so the units that we can use to represent omega, primarily you're going to be seeing radians per second. These are the SI units that are associated with it. However, we could also see this in degrees per second. We've got revolutions per second or revolutions per minute, mostly seen as RPMs. All of those are valid ways of representing units of angular velocity. Okay? This, in words, means to us the average angular velocity, the instantaneous angular velocity, is the rate at which a particle's angular position is changing as it moves around a circle. So the rate at which angular position is changing around a circle. All right. Now, in uniform circular motion, we're looking at a constant angular velocity. Okay. Now, graphically, this is the same relationship as position and velocity. Remember, we can obtain velocity from the slope of a position versus time graph. So, likewise, we can obtain omega from the slope of an angular position versus time graph. Okay? Now, if you recall, when we write the equation of a line on a position versus time graph, we end up with this equation of constant velocity, which looks like this right here. This is one of the first equations that you learn about in physics. We can get the exact same equation from an angular position versus time graph. All it's going to look like, though, is the final angular position is equal to the angular velocity times time plus the initial angular position. All right? So this is where theta f is equal to final angular position, omega is equal to angular velocity, and theta initial is the initial angular position. All right. Now, just as a reminder, I talked about this briefly in class today. When you have your circle here, all right, if that circle is rotating counterclockwise, so in that direction, counterclockwise rotation, we're going to have a positive angular velocity. Whereas clockwise rotation, or in this direction, is going to have a negative angular velocity. So let's look at this on a graph. All right, let's check out a graphical representation. So graphically, we're going to put angular position on the y-axis, and we're going to put time on the x-axis. Alrighty, time in seconds, and our angular position again is in radians. And so let's say that we've got some motion as follows. Let's say that we've got up to here, then we come down, and then we go here. All right, and let's define some points here. So let's say that this point right here is going to be 3 seconds at position 6 pi, and this right here can be 4 seconds at position 4 pi, and this is 6 seconds at position 4 pi. All right, now remember that 6 pi, we can think of one rotation as being 2 pi. So one revolution is equal to 2 pi radians. Therefore, 3 revolutions would be equal to 6 pi radians. All right? So the first thing that we're going to do here is we're just going to describe the motion. All right? So looking at this, what this first section of motion tells me here, so the first section, I'm meaning this section right here. That section of motion tells me that in 3 seconds, I rotated 3 times. Okay? So we can calculate this, and we can say from time is equal to 0 to 3 seconds, I want to calculate my angular velocity. So my slope is going to be equal to my change in theta over my change in time. This is equal to 6 pi radians divided by 3 seconds. 6 pi radians divided by 3 seconds tells me that I'm rotating at a rate of 2 pi radians per second. We can also think of this as 1 revolution per second. Okay? Now, this is rotating counterclockwise, and I know this because this pi is positive. Now, because that pi is positive, I know that I must be rotating in the counterclockwise direction. Okay? Now, I can do the same thing for these other sections of motion here. So from t 3 to 5 seconds, if we look at that, we're going to do the same calculation from 3 to 5 seconds. And from 3 to 5 seconds, I end at 4 pi, but I started at 6 pi. I'm sorry, I'm going to do 3 to 4 seconds here, 3 to 4 seconds. I started at 6 pi and I ended at 4 pi. And I ended at 5 seconds and started at 4 seconds. So I'm going to get this as negative 2 pi divided by 1 second, which tells me that I'm rotating negative 1 revolution per second. So in this case, here I'm rotating counterclockwise, here I'm rotating clockwise, because that angular velocity is negative. Okay? Now, after I hit 4 seconds. I'm sorry, I messed this up here. This is supposed to be from 3 to 4 seconds, so 4 minus 3. All right, so this final section here, you can think of it just like you would in a position versus time graph. So in this section on a position versus time graph, my slope is equal to 0, which would mean I would have a 0 velocity. Well, it's the same thing on a angular position versus time graph. My slope is 0, therefore my angular velocity is 0, or 0 radians per second. All right? Now, let's compile all of our information here. So from t is equal to 0 to 3 seconds, I had an angular velocity of 2 pi radians per second. From t is equal to 3 to 4 seconds. Keep messing that one up. From 3 to 4 seconds, I had an angular velocity of negative 2 pi radians per second. And then t is equal to 4 to 6 seconds, I had an angular velocity of 0 radians per second. So from this information, I can make an angular velocity versus time graph. So let's go ahead and do that. So if I make an angular velocity versus time graph, I'm going to be plotting angular velocity on my y-axis, and then I'll be plotting time on my x-axis. So let's change these colors here. So we got time in seconds, and then we've got angular velocity in radians per second. So I go as high as 2 pi radians in the positive direction, so we'll make this 2 pi, make this pi, and then I go negative 2 pi in the other direction. So here's negative pi, negative 2 pi, and I need a total of 6 seconds. Okay. So from 0 to 3 seconds, I had a constant angular velocity of 2 pi radians. All right, so I'm going to make that a constant 2 pi radians for 3 seconds. And I don't want that arrow there. So we just got something that looks like this. And then from 3 to 4 seconds, I had a negative 2 pi there. And then from 4 to 6, I had 0 there. So looking at this in total, what we end up seeing is a graph that looks pretty much exactly what we would see on a velocity versus time graph, except here we're looking at it in angular velocity versus time from angular position. Okay? So some things that we can derive from this. An expression that we can get from this is that the absolute value of my angular velocity, so the absolute value of my angular velocity, we can think of as my angular speed. So this is going to be equal to 2 pi radians divided by 1 period. Or I can rearrange this and say that 1 period is equal to 2 pi radians divided by the absolute value of my angular velocity. So let's look at an example of this implemented. So in this example, we're going to have a ball rolling counterclockwise inside a 30 centimeter wheel. So ball rolls counterclockwise along a 30 centimeter wheel. Some things we know. The ball completes 2 revolutions in 1.2 seconds. So we want to know angular velocity, and we want to know the position at time equals 2 seconds. And our initial angular position is equal to 0 radians. So those 2 things we want to figure out. All right? So let's focus first on part A. Part A, we want to figure out the angular velocity. Now this piece of information is important to me. I can complete 2 revolutions in 1.2 seconds. So from this, I can figure out my period. All right? Now, if you'll recall from our previous conversation, a period is the time it takes to complete 1 revolution. Okay? So in order to figure out the time it takes to complete 1 revolution, I'm going to do 1.2 seconds divided by 2 revolutions. And this is going to tell me that it takes 0.60 seconds to complete 1 revolution. All right? That right there is equal to my period, represented by t. All right? Now, what we just talked about, a way to calculate angular velocity, is to use this equation right here. So looking at this equation, omega is equal to 2 pi radians divided by t. Well, I now have t, so I can say 2 pi radians divided by 0.60 seconds. It's going to be equal to 10.47 radians per second. Now, that isn't crazy helpful to us, but that is our angular velocity. All right, so let's talk about what this means. 10.4 radians in 1 second, because it's a little bit hard to conceptualize what 10.47 radians is. All right, so let's remember that 2 pi radians is equal to 1 revolution. All right, now 2 pi is about equal to 6.28. So looking at 10.47 radians per second, that means that we're almost doing 2 full rotations in 1 second. And that makes sense based on what we were given, because here it says 2 full rotations in 1.2 seconds. So our answer of 10.47 kind of makes sense. Now from here we can move on to the part B, position at time equals 2 seconds if theta initial is 0 radians. So looking at part B, theta initial is 0 radians and delta t is 2.0 seconds. So now we're going to go back to the equation we talked about earlier, this one right here. All right, this is going to come in very handy for us. So we can come over here and say that theta final is equal to theta initial plus omega times delta t. I know theta initial, I know omega because I just solved for it, and I know delta t. So now we can plug in and say theta final is equal to theta initial, which is 0, plus omega, which was 10.47 radians per second, times delta t of 2 seconds. So I get that my final position is equal to 20.94 radians. All right. Now, 20.94 radians, again, not crazy helpful to us. So here's what we're going to do. We can say theta final is equal to 20.94 radians, and I'm going to divide that by 2 pi. The reason I'm going to divide this by 2 pi is so that I can see how many revolutions I got. So this right here is equal to 3.333. And what this means is I had 3.33 revolutions. So I could also say that my theta final is equal to 3 complete revolutions. So we could say 3 times 2 pi radians, because that's 2 pi represents 1 revolution, plus the remainder, 0.33 times 2 pi radians. All right, so here I completed 3 revolutions, and then 0.33 times 2 pi is 2.09. So I was 2.09 radians into the 4th revolution. All right, guys. Thank you so much.